So we just saw how the Dyson series is the formal solution to the equation of motion for the time evolution operator. The other ingredient we need in developing perturbation theory is to study the structure of the interacting vacuum. So what we want to do is that we want to express the interacting vacuum in terms of the vacuum of the free theory. So we have the interacting vacuum, which is this omega. And we have the free vacuum. Now, one thing that we do assume is that the overlap between the interacting vacuum and the free vacuum is non-zero. That somewhere in our Hilbert space, these two states have some sort of overlap. So having done this, what we can do is that we can express the free vacuum in terms of the eigenstates of our Hamiltonian. What does it mean? So we have a Hamiltonian. So this is the interacting Hamiltonian, and it has energy eigenstates, which we can denote by n, and that will give me En n. The interacting Hamiltonian, E0 is the lowest energy state. And it corresponds to this state. So, and not the zero state. But if I take the vacuum of the non-interacting theory, we can now express it in terms of the eigenstates of the interacting theory. Of course, the first expansion would be this, and then there'll be the higher states, the higher energy states. So the sum will be from 1 to infinity, and here I have n, and the overlap between n and 0. So what then we do is that we apply the time evolution operator of the total theory for some time t, where t is a large time, onto the free vacuum. And then what we do is that we take the limit where t goes to 1 minus I epsilon times infinity. So what does this mean? This means that, if I look at the time plane, so this is t, so this is t, and this is the time, it's a complex plane, so I'm considering time to be a complex variable. Then what we're doing is that we are taking and we are just like slightly, tilting the time axis in this direction. So anyway, so what we do is that we take this limit, and it's a formal limit, and it doesn't necessarily have a physical interpretation, but but it has a very nice result. It does something very nice for us, and let's see what that is. So we take this limit, and then we apply. So if I look at this in this limit, what do we have? The first term gives us e to the power minus I e of 0 times t times omega times the overlap of omega with 0. And then we also get all the other terms where n goes from 1 to infinity. And here we will have some exponential of minus I e of n of t acting on, well, it's a number times n0. Now, because the time has a small, negative imaginary part, and which I wrote a small rotation, we see that if I look at the imaginary part of this factor, what we find is that there's going to be minus I epsilon here. So minus I epsilon times minus I will give me minus epsilon times infinity. So that means that this is going to be strongly suppressed. This will also be strongly suppressed, but since E0 is smaller than any of the ENs, the suppression of this term will be much less than the suppression of this term. So in this limit, what we can do is that we can then drop all these higher order terms. So if I drop all these higher order terms, then I get in the limit where t goes to 1 minus I epsilon times infinity, we get the overlap between the interacting vacuum and the free vacuum times e to the power minus I 0t times omega. And then from this, I can write omega in terms of the free vacuum, and that's going to be given by limit of t goes to 1 minus I epsilon infinity. And then I'll have a numerical factor, which is going to be omega 0 e to the power minus I, E0 of t inverse times e to the power minus I, h, big T acting on the free vacuum. But for t very large, we can then shift t by t plus some finite amount of time, t0. Then we can write omega as limit t goes to 1 minus I epsilon infinity. And then here I get omega 0, and in the exponential I get minus IE 0 t plus small t0 inverse e to the power minus I h t plus t0 acting on the free vacuum. And then what we can do is that we can write this as, so we have the same limit and all of these things, the numerical factor, I just write it in this bracket. And then we can write this thing as an exponential of minus IH from T0 minus of big T. And then remember that the free vacuum is an eigenstate of H0 of 0 eigenvalue, and therefore we can multiply the free vacuum by an exponential factor, which involves a free Hamiltonian. So we can write this guy as exp to the power of minus I h naught minus t big T minus small t0 acting on the free vacuum. And this, is equal to this because we know that H0 acting on the free vacuum is just 0. So if I expand this, only the first term survives. So we recognize now these two guys as giving us the time evolution operator. So we recognize this as the prefactor times the time evolution operator from minus t to t0. So here's a little proof of this. So recall that our definition of the time evolution operator t from t0 to t has two exponential factors. One is the exponential factor of h0, and h0 is multiplying t minus t0. And the other one is the exponential factor of minus I of h. H is the full Hamiltonian, and this will have t minus t0 as well. So using this, what we can do is that we could write u going from with t0 to minus t is going to be equal to exponential of I h naught, and here we get minus big T minus t0, and then that multiplies exponential of minus I h minus big T minus t0. Now we know that if I change the ordering of the time in the argument of the time evolution operator, that is equal to taking its inverse or the Hermitian conjugate. So that is, I can just switch the argument of the time evolution operator, and that means that I'm taking the original time evolution operator and taking its Hermitian conjugate. So if I do this, then I find that if I take the Hermitian conjugate of this expression, it'll reverse the order so that what I'll get is that I'll get the exponential of plus I h of minus t minus t0 first, and then I'll get exponential of minus I h0 of minus t minus t0. Argument should have been t0 minus t. So we have shown that our interacting vacuum up to a numerical factor is this object acting on the free vacuum. So similarly, one can show that if I take the bra of the interacting vacuum, that can be expressed in terms of the free vacuum, the bra of the free vacuum. Again, the limit to take is t goes to 1 minus I epsilon infinity. And here we will have omega, I think we get, we get 0 omega e to the power minus I e0 t minus t0 inverse, and then this is 0, and there's u acting on t on 0 from t0 to t. So these are the expression of the interacting vacuum in terms of the free vacuum. Next, we put